Well, this presentation belongs to the course assignments playlist, and in this case it relates to the final coursework that is proposed for this year's edition of our Software Hardware Co-Development of Embedded Systems course. Please recall that it accounts for 25% of your final grade. And notice that it addresses the 1149.1 boundary scan test domain. So you should revisit the presentations addressing this topic in our course syllabus. It was actually the first topic that we considered, and the corresponding presentations are still available in the appropriate playlist in our lesson pages. It is important that you start by revisiting them, or otherwise you may not understand the objectives of this final coursework. Now, after watching this presentation, you shall be able to explain what are the objectives of this final coursework, and also to present the functional specifications of the system that is proposed here. And you should be able to set up a plan to begin your work. The envisaged deliverable may be represented as you see in this slide, so we will have a custom architecture that will be implemented differently according to each group. And this custom architecture will run a test program that is stored in the local FPGA memory. Now, this test program comprises a number of commands and data that will have been received from the PC using a communications channel of your choice, and so the appropriate communications module will have to be implemented in the FPGA as well. And the whole system will be implemented in the Nexus 3 FPGA board. Now, your custom architecture will control the test access port of the boundary scan board under test. So it must generate the bit stream to shift into the test data input pin, and at the same time generate the appropriate signals for the test mode select and test clock pins. And whenever that is required, it should read the bit stream coming out from the test data output pin and compare it with their expected results. Now, the minimum functional features of our test controller are shown in this slide. So it comprises at least one test access port. It should accept serial vector format like commands. Serial vector format is a test representation language that was developed jointly by Texas Instruments and Teradyne, and you can read more about it at this Wikipedia page. Our system should receive the test code from the PC using a communications channel of your choice, as has been said. And it should support one push button for running the test and two LEDs to show the test result, either pass or fail. Now, the source code comprises this set of commands shown in this table. Reset, as the name indicates, is used to reset the boundary scan logic, so it will take the BST logic into the test logic reset state. TMS0 and TMS1 will be used to move from one state to another in the test access port controller state transition diagram. Shift will be used to scan a bit stream called X containing n bits into the selected scan chain. And shift and compare is an equivalent but more sophisticated version which, besides scanning data into the selected scan chain, will also read the data that is coming out and compare it to the expected bit stream Y using a mask information that is stored in bitstream SETA. So for each bit that is shifted into the board, the bit coming out from TDO will be compared with its expected value as represented in Y, and an error will be generated if the two values are different and the mask bit for that position is active. Finally, there will be a multiple TCK command which generates multiple TCK pulses while keeping TMS at 0. And finally, end of program is not really a command, it simply marks the end of the object code. So we will have to convert our source code into object code, and for this purpose we will use a universal cross-assembler. In this case I propose that you use the Telemark universal cross-assembler TASM. This is a shareware application that uses a table to relate the source commands to the corresponding object code. This command, this table is simply one text file that we build with this content, and every time that we run the assembler, it will take the source code, use this table, and then produce the object code containing the operation codes indicated in the table. Now, of course, this allocation between source and object codes was entirely arbitrary, and you can choose any allocation by yourself. So the test workflow comprises 4 main steps. We will start by writing the source code using the SVF-like commands that have been described. Then we will use the TASM cross-assembler to compile this source code into the object code file. And this object code that is generated by TASM uses the Intel X format, so the object code will be stored as a text file. And this text file comprising the object code will then be sent using the communications channel of your choice to the PicoBlaze memory. Finally, when we press the Run button, the test program will be executed and the LEDs will display the result. So actually there are 3 main alternatives for implementing this test controller. We could envisage to implement it as a general purpose embedded core, be it the PicoBlaze or the MicroBlaze soft cores from Xilinx. It could be implemented as a microprogrammed architecture, or it could also be implemented as a finite state machine with data path, or FSMD. Now, what I propose here is that each group should develop one implementation, in this case the proposed allocation between the alternative implementations and the groups are shown in this slide, and prepare a presentation for a final workshop that will address profiling and performance evaluation of the 3 alternatives indicated here in this slide. So you will, each group will implement this functional specification using the implementation alternative indicated here in this slide, and then prepare these slides for the final course workshop. So the expected deliverables from this coursework comprise code files, be it in VHDL and assembly or C, according to which embedded core you select. The VHDL will be used, for example, for the communications module or for the local memory. And you will use assembly if you select the PicoBlaze, C if you select the MicroBlaze for the embedded cores. The expected deliverables will also comprise test benches, in this case VHDL test benches for simulating your intermediate architectures, and also SVF program is used with the prototype board. And finally, you will also deliver a set of slides for the final course workshop. So how do you start? There are possible ways to go. One of those ways is shown here. You should, or you might, start by drawing a state chart for the implementation of each test command. That is to say, reset, for example, corresponds to setting the TMS output to 1 and then driving 5 clock pulses at TCK. So you can draw a state chart representing the sequence of elementary operations that correspond to the execution of this test command. And that is a formal representation of how each SVF command will be executed in practice. You should also define the memory organization and the communications protocol, and this requirement is common to the three alternative implementations that were represented in the previous slides. And likewise, the communications hardware and the memory module will also have to be implemented, whatever the implementation alternative that you select. And finally, you have, of course, to design the necessary logic structures and the code for the implementation of each SVF command. Please keep in mind that it is of vital importance that you split the tasks within the group and set deadlines for the work of each one of you. Now, in this final slide, I leave you a set of possibilities for taking this work further, in case you wish to do so.